Here's a useful theorem that shows another special property of conservative vector fields, the loop property of conservative vector fields. So TFAE, that's an abbreviation for the following are equivalent. So the following are equivalent means that if you have a vector field with property 1, it also has property 2, and then you have a vector field with property 2, it also has property 1. What are these properties? Property 1 is that the integral over C of f dot dr is equal to 0 around every closed loop in your domain D. And property number 2 is that f is conservative on D. And so remember, conservative means that the integrals are path independent. Let's actually prove this. This won't be too difficult to prove. So in order to prove this, we need to show that if statement 1 is true, and the statement true is 2, and if statement 2 is true, and so is statement 1. So first, to show that statement 1 implies statement 2, so we're given that the integral of f dot dr is equal to 0 around every closed loop. We want to show f is conservative. So conservative means that f dot dr is path independent. So what we're going to do here, pick any points A and B. And we want to show that the integral from A to B is path independent. So let's have, here is one path from A to B. And here is another path from A to B. And so the thing that we want to do is we want to show that the integral from A to B along C1 is equal to the integral from A to B along C2. But we know that we're assuming this first statement here, integral around any closed loop of f is 0. Do we see a closed loop here? Well, we can go along C1 and then go along the negative of C2, and this gives us a closed loop. So the integral, I'm going to make up a little bit of notation here, C1 of f dot dr minus, we're going in the wrong direction, quote unquote the wrong direction, the opposite direction along C2. So that becomes a minus integral along C2 of f dot dr. This is equal to 0. Rearrange, move this to the other side. This shows that the integral of along C1 of f dr must equal the integral along C2 of f dot dr. And so this successfully shows that our our integrals here are path independent and the field is conservative here. So that's good. Now we need to show the other part of this. We need to show that if f is conservative, then you get the integral around every closed loop of f is 0. So what do we do? Well, let's just say that we have this closed loop here. We want to show the integral around this closed loop is 0. How do we do that? Well, let's just pick 2 points here. Let's call this A, and let's call this B here. And so, we're free to do this. Let's say that this right here, that chunk is C1. And let's say that that chunk there is C2. So now C is equal to C1 union C2. Well, we want to have 2 different paths going from A to B. Because we're assuming f is conservative, so that means as it's path independent. We've got one path going from A to B along C1. C2 is going from B to A, but we can do negative C2 from A to B. And so because f is conservative, we have the integral along C1 of f dot dr must equal to the integral along negative C2 of f dot dr, because we're assuming that f is conservative. Conservative means that the integrals are path independent. So now we move this to the other side of the equation here. Integral along C1 of f dot dr minus the integral along negative C2 of f dot dr must equal 0. But the integral over negative C2 of f dot dr is equal to the negative of the integral over f dot dr. So minus times minus integral over the original C2 of f dot dr must equal 0. Minus times minus is plus. And so we have that the integral over C1 of f dot dr plus the integral over C2 of f dot dr is equal to 0. But C is just, by additivity, this is just the integral over C of f dot dr, and this must equal 0. So this gives us this very nice loop property of conservative vector fields. If you know that your vector field is conservative, then you know that the integral over any closed loop, of your vector field must be 0. Let me just say something. What happens to your vector field is not conservative? What can you say about integrals over closed loops? Well, that's what we're going to be talking about in the next section. Okay, to finish off this video, let's just do a quick example here. The f of xyz is equal to xy times sine of yz. Evaluate the integral over c of the gradient of f dot dr, where c is parameterized by r of t is 4 sine t, 5 cosine t, 7 sine t minus cosine t. T runs from 0 to 2 pi. Now, I specifically cooked up this example here to illustrate how nice this loop property makes our lives. Because if we didn't have this loop property, what would we be doing? Well, first we'd have to take the gradient of f here. That would take some work. We've got our r of t. We need to find r prime of t. We'd have to substitute an r of t into the gradient of f that we had there. We'd have a dot product to do with the derivative of r of t. Then we'd have to integrate. That would be a lot of work. However, the loop property is going to make our lives easier. We just have to realize that there's two facts that we need to realize. So fact number one is that we need to realize that this is giving us a closed loop. R of 0, 4 times sine of 0 is 0, 5 times cosine 0 is 5, 7 times sine of 0 minus cosine 0 is negative 1. And r of 2 pi, that's our ending point here. R of 2 pi is equal to 4 times sine of 2 pi is 0. 5 times cosine of 2 pi is 5. 7 times sine of 2 pi minus cosine 2 pi is negative 1. So this is a closed loop because we're starting and ending at the same place. And then the second thing to realize here is that the gradient of f is automatically conservative. So gradients are automatically, the gradient of a function of a couple of variables is automatically conservative. And so what do we conclude here? This answer must be 0. This answer must be 0 with no calculation needed.